Welcome to this lesson on Hess's Law and additive enthalpy changes. This is a fundamental concept in thermochemistry that helps us understand how energy changes occur in chemical reactions. Hess's Law provides a powerful tool for calculating enthalpy changes that might be difficult to measure directly in the laboratory. Hess's law states that the total enthalpy change for a reaction is independent of the pathway taken from reactants to products. In simpler terms, it doesn't matter whether a reaction happens in one step or multiple steps. The overall energy change will be exactly the same. This is because enthalpy is what we call a state function, meaning it only depends on the initial and final states, not on how we got there. Let's visualize this concept with a simple example. Imagine we want to go from A to C. We could take a direct path from A to C, or we could take an indirect route going from A to B and then from B to C according to Hess's law. The total enthalpy change for both pathways will be identical. This path independence is what makes Hess's law so useful in chemistry. Mathematically, we express Hess's law using this equation. The total enthalpy change equals the sum of enthalpy changes for each individual step. So delta H total equals delta H1 plus delta H2 plus delta H3, and so on. This means we can add up the enthalpy changes of smaller, known reactions to find the enthalpy change of a larger, more complex reaction. Let's work through a concrete example to see how this works in practice. Suppose we want to find the enthalpy change for the combustion of carbon to form carbon dioxide. The target reaction is carbon solid plus oxygen gas forming carbon dioxide gas. But instead of measuring this directly, we'll use Hess's law with intermediate steps. We're given two separate reactions with their enthalpy changes. Step 1. Carbon solid reacts with half a mole of oxygen gas to form carbon monoxide gas, with delta H1 equal to negative 110 kilojoules. Step 2. Carbon monoxide gas reacts with another half mole of oxygen gas to form carbon dioxide gas, with delta H2 equal to negative 283 kilojoules. Notice how these intermediate steps, when added together, will give us our target reaction. Now we apply Hess's law. The total enthalpy change equals delta H1 plus delta H2. Substituting our values, we get negative 110 kilojoules plus negative 283 kilojoules. When we add these together, we get negative 393 kilojoules. This is the enthalpy change for the direct combustion of carbon to carbon dioxide, calculated using the indirect pathway. Let's summarize the key points. First, enthalpy is a state function, which means it only depends on the initial and final states. Second, the total enthalpy change depends only on the initial reactants and final products, not the steps in between. Third, the pathway taken does not matter for calculating enthalpy changes. And finally, we can add individual step enthalpies together to find the total enthalpy change. Understanding Hess's law is essential for solving more complex thermochemistry problems.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.